Well, as Norm has outlined, we're working, I would say, from above through the space of possibilities to define the questions and options that are remaining before us. So I'm actually at a little bit of a disadvantage here because I can't read that monitor and I don't have a paper copy. So
you can take mine.
Computer.
No. This one?
no, that's I'll do it.
Oh,
from
this
my
is Sal's, right? I didn't get
Excuse me.
No, I don't have.
It'll take just a second. Well, okay. So the topics of this first discussion, which I'll lead us through, which is largely review to set the stage for the next three discussions we'll have, is to summarize the potential decisions and options on human exploration. And this will lay the groundwork for the discussion that will immediately follow me from Sally Ride on the costing and scheduling work that has been done to date on these by the combination of the aerospace and NASA team. And then my colleague Wanda Austin will present the framework in which we're going to evaluate these, and then there'll be a committee discussion of the actual evaluation process that will follow that. So just to quickly summarize, we've reduced the number of questions that a policymaker would face in resolving this issue of future human spaceflight now down to 5 by reflecting on the deliberation that occurred at the last public meeting and simplifying and combining some things. So essentially, the questions are, what's the phase-out plan of the shuttle? Should it fly out the remainder of the flight safely? That would be the minimum that we would recommend. Or that we should extend it 1 or 2 shuttle flights per year through about 15, which would likely only be a desirable idea if it was done in conjunction with a tightly shuttle-derived vehicle used for heavy lift. Then second, what's the future of the ISS? Should we retire it as planned from the U.S. human spaceflight plans in 15 or extend it to 20? So, oh, I'm sorry, that was the chart I just covered. So we'll synchronize here in a moment. So I'm just going to have a quick chart or so on the possible variants of these decisions that we're still considering. There is, as it is shown by NASA, a little margin left in the shuttle schedule, and there's broad agreement that the important thing to do is to fly the remaining flights safely on a schedule that will unfold from flight to flight, and that we estimate that this will go sometime at least into fiscal year 11, if not into calendar year 11. It's the safe and appropriate thing to do, and we recommend nothing other than doing this at a minimum. The only problem with this is, of course, that the additional funding in FY11 to extend the lifetime of the shuttle transportation, the space transportation system, is not currently in the budget. So at an absolute minimum, we will recommend that that be included. Then the question arises, should we so-called close the gap from below and extend the shuttle to about 2015 or sometime in the mid-decade, by which time some other US-based capability would be available to fly to the ISS. We think that this can be done safely at a flight of 1 to 2 flights a year, that this would make sense economically if tightly coupled with a heavy lift option that most directly built on the shuttle heritage. It would reduce the gap. It would support the continuing utilization of the International Space Station, which was in fact designed assuming that the shuttle was available for a logistics carrier. It would smooth some workforce transitions, and it would make maximum advantage of existing infrastructure. However, it is not in the budget as defined by the President or by NASA going into this point, and it would require the extension of the shuttle systems throughout this approximately 5-year period, which would, of course, impact all of the other plans that are also in the budget. In addition, there's a technical issue, which is that although the shuttle has been gone through phased reviews of its continuing airworthiness or flightworthiness, we would recommend some additional NASA and independent risk assessment associated with the technical issues, aside from the budgetary and programmatic issues, of extending the shuttle lifetime. Did I say that about right?
Yes, sir.
Okay. Oh, yes. I'm sorry. I'm not nodding at the right time, right?
You might read the shuttle slide time.
Yeah, right. Good idea. Thank you. So now I'm on ISS to 2015, which is one more. There we go. So that's really the two options that we're considering in the shuttle. Retire it in a workmanlike manner when the existing flights are flown out in probably 11, or extend it to about 15. Now we come to the next decision, which is what's the plan for the ISS? And here the, if you will, reference decision is to continue with the historical plan, that is to say the plan which is in the current budget, of ending primary U.S. support for the ISS in 2015. And that we would focus to the greatest extent possible the work there on both the continuing science and the preparation for exploration. That the resupply and logistics between now and then would likely be through the international partners and through the commercial transportation services contract. That is to say that it's our view that it is unlikely that any other U.S.-based capability, either government or commercially provided, would so-called close the gap from above. That is to say, would be available substantially before 2015. If we proceed with this, it would require, since the International Space Station is a truly international endeavor, would require an agreement among the partners for the either extension or decommissioning and retirement of the station. What this essentially, this option essentially would probably lead to is the retirement and deorbit of the ISS in 2016. Our view being that it is unlikely that there is a managerial solution or a non-U.S. lead user solution that would allow the station to function in a robust way without the involvement of the United States government. So essentially, we have not found a desirable solution which is allows the space station to continue past 15, but without the United States being the lead user and carrying that line within the budget. Although we looked hard. The alternative is to extend the ISS until about 2020, or at least until 2020, which would allow what we are calling enhanced U.S. participation. In the budgeting for this, we've actually put in a more robust budget line for utilization of the space station, and this would show to our partners a full commitment to utilize the space station at least through the first decade of their presence, many of whom only placed their laboratory modules on orbit in the last year or so. That this would provide additional opportunities for international partnership. One can imagine including new partners and using the ISS partnership as an evolving mechanism by which a more standing partnership, a more established partnership would then be transitioned from the use of the ISS to a partnership for exploration. This is something that the international partners have said to us they think would be a desirable path. In this case, there would be an extensive utilization of the ISS, both from a human physiology perspective and from an engineering development perspective, to lay the groundwork for exploration. Things like the development of cryogenic fuel handling and transfer in zero gravity would be likely to be developed and tested on the station through this enhanced utilization program. And this option is actually more consistent with the existing national policy of viewing the ISS as a national laboratory. However, it is not consistent with the existing budget, which does not contain funding for the space station past 2015, and in fact, probably also does not contain enough money to retire, that is to say, deorbit the space station in 2015 or 16, if that were the choice. So in our, as Sally will discuss, we've appropriately put in reserves into all of our budgeting exercises for either the extension or the orderly deorbit of the space station. So that covers the decisions, the first two decisions, what to do with the shuttle and what to do with the ISS. Now, these two are somewhat closely coupled because they basically have to do with launch into low Earth orbit and the servicing of crew in low Earth orbit. The first one is should the government develop launch system be based on NASA/Shuttle heritage or an EELV-based system? So we essentially are now carrying four choices for that decision. The program of record, the Ares 1 plus Ares 5, without any explicit considering of on-orbit refueling, a proposal that actually came from the program that we slightly scale back the capabilities of the Ares 5 to what we call the Ares 5 Lite, to keep it simple. There is an official program designation for this. And that you would use this, for example, on lunar missions in a dual launch scenario where two launches of the heavy launch vehicle rather than a launch of the Ares 1 and the Ares 5 would be used to support lunar missions. And in this one, importantly, the Ares 5 would become human-rated, or at least human-ratable. And this option would be enhanced with potentially commercially supplied refueling in low Earth orbit, at least initially in low Earth orbit. The third principal option here is the directly shuttle-derived vehicle, one that would be either side mount or inline, but would trace more directly to the NASA heritage of engines, SRBs, external tank, and so forth, which also could be potentially enhanced with on-orbit refueling. And the last option we are carrying is an ELV heavy, an ELV super heavy, something in the 75 metric ton category, which is really a placeholder for a more generic hydrocarbon-based rocket, which would have a LOX kerosene first stage and high-energy LOX hydrogen upper stages, something along the layout of, not necessarily the physical layout, but the fuel choices that were used in the Saturn V. And it, too, could be potentially enhanced by commercial refueling. So you'll see that in actually all the cases, but the baseline, the first one, we are considering recommending that the technology for on-orbit fuel transfer of the appropriate fuels, in all cases LOX hydrogen, be developed as a technology item so that it would eventually be available to either increase the throw mass from low Earth orbit of the smaller stages or enhance the throw mass from low Earth orbit of the larger stages.
I think there's a business model choice that's embedded in that too, not just a technology.
Yeah, and I'm actually, I'll get to that in the chart. Thank you, Jeff. And then the other question is, how should the crew be carried on U.S. government-provided systems or by commercial and internationals? And in this latter case, it implies that we think that the U.S. government should maintain an option for the future of being able to fly crew to low Earth orbit in the case that either for one reason or another the internationals or the commercials do not materialize or are no longer interested or able to carry them, but that what we've decided to recommend is that this is an operational backup. That is to say that whatever the vehicle that is chosen in answer to question 3 should maintain the capability of at least being human rateable without a great deal of additional investment. So there would be some cost in both performance and money to doing that, but it would retain for the United States the option of having a government provide access to low Earth orbit. So in a little more detail, here are the options. This is the Ares 1 plus Ares 5. This is essentially the program of record, about a 26-ton vehicle and about a 160-ton vehicle using NASA heritage components. Oh, I'm sorry. Thank you. Just bug me for Leroy when I forget that. That the Ares 1 would be the crew transportation to ISS and Earth orbit, that in the Lunar and other out-of-LEO missions, it would rendezvous with the Ares 5 in crewed flights, and the Ares 5 by itself would be used in cargo flights. A slight variant of that, as I mentioned, is the one proposed by the program to simplify or scale back the design of the Ares 5 a little bit, going from 5.5 to 5 segments, from RS-68Bs to RS-68A engines. This reduces the performance a little bit, but still keeps it in this sort of super heavy class. But along with this, you would redesign the mode for lunar exploration to be the so-called dual launch, where, well, there are various manifesting options. I won't go into that detail. But as a cargo vehicle, now you would launch one Ares 5, and in crewed missions, you would launch two in a dual mode. And there are options here for the rendezvous occurring either in Earth orbit or in lunar orbit, which is a matter of some details of the balancing of the payload on the two launch vehicles. We have costed and are still considering a directly shuttle-derived vehicle as an option. And we have not made...
Ed, would you call, excuse me, would you call by numbers so these folks can, you know, cycle the charts?
I'm sorry.
Thank you.
So that was chart 10 that I was just referring to. Now we're going to 11, right? Shuttle-derived vehicle. In this case, we have examined conceptually and still keep in the trade space both the side mount and inline shuttle-derived vehicles, because we do not feel that within the scope of this study we are likely to directly recommend that one or the other is the likely desirable vehicle if this class of launch vehicles remains in our recommendation. That's simply too detailed an engineering study that a panel of this size, even with the support of NASA and outside contractors, would be able to do during this time frame. However, we have kept it in the trade space as a generic option of a vehicle which is directly shuttle-derived and has performance in the range of 100 metric tons to LEO, and that neither of these would necessarily be human-rated, and that in fact we would use a commercial crew transport to bring the crew to low Earth orbit and transfer into the heavy lift vehicles and their payloads and inject out of low Earth orbit. So I guess this is an appropriate point to observe that there is a strong consensus that the government, the United States, should support a vigorous program of developing a commercial crew transportation launch vehicle and capsule that would be used, for example, in this scenario, and that would be the likely crew transportation system from the United States in the event that we extend the space station beyond 2015. So thereby creating, in addition to the COTS cargo capacity, which is currently under development, an additional broadly based commercial opportunity to supply launch vehicles and capsules for crew. And that this would be an open competition with good specifications written by the government and a largely commercially provided service. This is consistent with the discussion that the panel has had at several of its previous meetings, that the appropriate task for NASA is to do the hard things, to develop the new technologies. And in fact, going back to a model which is in the predecessor of NASA, the NACA, one of the primary roles of the NACA was to develop technology which was then transferred to commercial industry and that appeared in both military and civil aircraft. And we think that a reinvigoration of this, the hard job, the development of the big new vehicles and the technology to support the commercial exploitation of space is an appropriate task for NASA in the years ahead. This crew transportation vehicle would also be used alongside a LOX kerosene-based ELV Super Heavy vehicle in the 75-ton range. And again, the commercial vehicle would transport the crew to the ISS and do Earth rendezvous. There are several options for the Super Heavy with the LOX RP1-based first stage, and we do not intend to necessarily advocate any one of those potential routes for acquisition, or any one of the routes to a particular vehicle, that this is a generic class that we're considering. For the Moon, the crew missions for a vehicle of this class are likely to consist of the crew taxi and 2 or 3 launches, depending on the exact design of the lunar system that follows. And the cargo is 1 or maybe as many as 2 launches to provide the logistics train to the lunar surface and to other destinations beyond low Earth orbit.
Ed, may I make a comment? I think it's absolutely essential that if NASA undertakes this competition for crew access to LEO, that the competition is structured in such a way that not only the newcomers into this business can compete, but also our best and most experienced companies can likewise participate.
Right.
Because they'll give us assurance that we will have reliable access to space by our crews. So, and it's going to require a very wise, very smart structuring of this competition.
Right, absolutely. That's a broad consensus of the committee, I would say. Okay, and the last point on transportation is that we have spent a fair amount of time thinking about the opportunities that are created by either refueling with a single tanker the upper stages on orbit, or refueling from a depot of Earth departure stages in orbit. This is not a new idea, as Jeff showed at our meeting last week, wherever it was. Was it here? Oh, it was in Cocoa Beach, I think. A famous quote from von Braun, who in fact had imagined this operational concept, as he did many, and advocated it, that in the tanker mode, which is slightly simpler, a single tanker is launched to orbit. In the depot mode, a more semi-permanent or permanent depot exists, and in that case becomes the fuel tank in space. It becomes the repository for smaller or medium-sized vehicles, which could also be commercially supplied or commercially delivered fuel to orbit, to come up, meet with the depot, transfer fuel, and then there's an autonomous rendezvous, which would be an autonomous rendezvous and fuel transfer, and then the eventual cargo stage that is tanked would come up and rendezvous with the depot. This is the KC-135, KC-10 in the sky. It's exactly the same concept. You enhance the capability of the vehicles by independently having fuel arrive there and transferring it. The advantages of this are that for a given upper stage or departure stage, you can significantly, probably by at least a factor of 2, increase the throw capability away from the Earth, important if we plan to explore, or you can take it out in design and build a smaller Earth departure stage and resulting booster, and be able to inject an equal amount of mass out of low Earth orbit. The disadvantages are that the operations become more complex. There are more launches for a single event. There's some isolation of that problem by putting in a depot so that the flights to the depot become decoupled from the flights out of low Earth orbit. There are technologies which have to be developed. And this is a good point to mention also, that it's a strong feeling of the committee that in any budget that we go forward with, that a significant investment in new technology for space should be included. So this creates, this is the answer to your comment, Jeff, this creates a basically third potential market for commercial development of space. The first being the existing cargo supply to the space station, the second being the potential of commercial crew to low Earth orbit, and the third being the delivery of fuel to a tanker or depot. So this creates the possibility of a business model, as Jeff mentioned, which creates a fairly robust and dynamic demand for domestic commercial providers of launch services to space.
While I completely agree with all of that, the point I was trying to mention earlier is I think in our internal deliberations that when we've discussed the various 75 class ton alternatives, it's not just a technology choice about which fuel you put in the first stage. We're also looking at sort of a make versus buy model.
Yes, right. You're absolutely right. I was going to let Sally explain that. Got that, Sally?
Yeah, thank you.
Yeah. Well, let me expand on what Jeff has said. Is that within the class of vehicles which does not rely directly on Shuttle and NASA heritage, which would be, if you go to chart 10, would be either the Ares family or on chart 11, the Shuttle Derived family. Essentially, if those are the launch vehicles of choice, the business model is the current business model, which is that these are NASA-derived vehicles built, at least in part, in NASA-maintained and operated facilities. The choice of the heavy hydrocarbon, which is more aligned with the existing ELV and commercial launch infrastructure, creates the opportunity for the alternative business model that the launch services are largely acquired in a more commercial mode by NASA, even for the heavy lift vehicles. And is that the point? Yes. And Dr. Ride will comment on the economic and other considerations of that in her comments.
Ed, just, yes, you stated it as an opportunity, but there is also a flip side to it. We in America have gone hydrogen, oxygen for a long time. We have gotten good at it. We have gone solid booster for the first stage, where thrust is very important, less so than ISP, and we have gotten good at that. And today to recommend that we are transitioning from this well-honed, well-developed know-how and thinking this is going to be a picnic undertaking what the Russians have actually been very good at. It's, we are not stating all the pitfalls, and we need to be clear that this requires abandoning what we have become good at and undertaking development of new things. In fact, a number of years ago, when question came of getting a hydrocarbon engine for Atlas, we had to go to Russia to buy one because we did not have sufficient, efficient technology to do it ourselves. So we have to walk into this new opportunity with open eyes.
That's absolutely correct. And as all of us know, the likely first stage engine for this, in the absence of a large new American LOX kerosene engine development, would be the RD-180, a Russian-supplied engine. So that in our consideration of this, we're also factoring in, as you know, the cost and schedule risk of developing a domestic large LOX kerosene engine of a comparable class, let's say. And we definitely understand, your point is well taken, that for the last several decades, the United States has used as the high thrust, not necessarily highest ISP option for launch from the ground. It's certainly in the civil program, a combination of LOX hydrogen and solids, and this would be a different route. The last of the decisions, which is what is the first destination for exploration beyond LEO, We've tried to boil down into these 4, the moon with surface exploration, 14, I'm sorry. Right. 14, back one. What's the first destination for exploration beyond Leo? The moon with surface exploration focused on a base or on sorties, which then move towards the development of a base. A moon with a surface exploration focused slightly more on the global exploration, more of a scouting and reconnaissance and the establishment of shorter-term bases. Deep space, that is to say, visiting the nearby planetary bodies up to and including flybys of Mars without any immediate exploration of the planetary surface, but with the use of robotics in coordination, and then an option which goes first to Mars. So Norm, today we're down 128, if you counted that up.
Keep going.
Yeah, by the end of the day. So I'll just give you a few words about each one of these. These are not significantly changed from the presentation that we made at Cocoa Beach several weeks ago. The charge 15, yep. That so the one which we loosely call lunar base, which in fact is sorties, which likely leads to a lunar base, which is approximately the approach of the program of record. The Constellation program is that there'd be first sorties to the lunar surface, and then extended stays, building up the capability of a permanent human presence of crew on the lunar surface at a base-like facility in rotations of about 180 days, much like the crew rotation is today on the ISS. That there would be mobility from this site, which should be likely in the range of hundreds of kilometers, which sounds like a long way to drive on the lunar surface, but in fact does not allow you to cover a very large fraction of the lunar surface as exploration. One of the deficits of this strategy, that since you're at a pole, you're able to get insulation from the sun to generate solar power through the lunar night. It's like a little like being at the South Pole on the equinox. The sun is more or less always on the horizon, so that you can find locations that will allow you to generate electrical power most of the time. That habitation would be provided by a concept not unlike the ISS, with modules that are offloaded from landers and linked together. And that the emphasis in this would be understanding the lunar environment and its applicability to future human exploration, to develop the long stay human physiology information, to learn how to scout and to move mobily on a planetary surface other than ours. There is interesting planetary geology to do on the moon that would be a prime objective of the science campaign. Reliability in the systems, the suits, the rovers, the airlocks, and a systematic testing approach of our capability to live on a distant planetary surface, but one that is not so distant that within a few days you couldn't get back to the home planet. The architecture that goes with this is fairly well understood. Next chart, 16. It's basically the program of record reference architecture, that there be a launch and a half, that is to say an Ares 1 and an Ares 5, that rendezvous in low Earth orbit. The Orion moves over and joins the stack, is injected to lunar orbit. The lander goes down to the lunar surface after some amount of time. The ascent module, if it's a crewed flight, comes back up to low lunar orbit, and the Orion capsule returns to a nominal water landing. In the cargo mode, you just take off the Orion and the ascent module. So this is a view of how, in reference years just starting from 1, so that we're allowed to slide it back and forth on the schedule, how this would be evolved, that in the first year you'd have human lunar return, a single flight for about 7 days on the lunar surface for up to 4 crew. By the second year, you'd have flights of up to 14 days with some initial power and habitation and mobility. By about the third year, longer distance pressurized rovers would be on the lunar surface, providing 14 or so day traverses on the lunar surface. And eventually, by about year 6 or so, you've established the capability of nearly continuous or continuous human presence, and then you continue to build up capabilities from that. There are mixed in here the option of making short duration, order of 7-day sorties to other sites on the moon of interest. So another strategy for exploring the moon we call Lunar Global, and this allows the evolution of the lunar surface exploration to proceed more in a long sortie or brief habitation mode. That we start out by some number of sorties of up to 7 to 14 days to various sites on the moon, which are of important scientific interest. And then we, in subsequent sorties, build up more and more capability that's deployed to the moon of habitats and rovers. This has the advantage that you then have this several hundred kilometer survey distance from a number of sites on the moon, so that you don't just go once to the pole and then are able to explore on the surface from there. And it has the disadvantage of not as effectively utilizing the assets that you brought to the surface of the moon on return visits. And there are some hybrids that go between the lunar global scenario and the base scenario, but these sort of represent the bookends in the system. So in the sortie phase, there might be 3 or 4 sorties to like number of locations, about 7 days. In the extended duration, you went to a first site, you might stay 50, 60 days. I'm sorry, I'm on chart 19. Thank you. That you would have come along with a cargo and some number of crewed flights, probably about 5. Then at the next site, you would push it up to maybe as much as 90 days with a couple of cargo flights and maybe as many as 6 crew flights and pressurized mobility, and so on. That you would, as you went to the next site, deploy increasingly more capability, and at some point, this strategy for exploring the lunar surface might just go back to the first one. At some point, you've found a place which is so interesting that you decide to build an almost permanent crewed base at that site. So these are not completely different strategies, they're slightly different strategies. So this would be what the timeline would look like for this Lunar Global. There'd be test flights and some sortie flights, maybe as many as 5. Then you'd go to the first extended duration location in years 4 and 5. With some habitation, you'd go to the second and unpressurized rovers, much like we used on Apollo. The latter Apollo flights, you'd go to the second location with some more habitation and pressurized rovers for traverses, and so on, building up capabilities. We're also still carrying the option of going first to the moon, first to Mars. We have stated for the record that we feel that the ultimate goal of human exploration is to become a spacefaring civilization, that the likely intermediate destination of that is on Mars, and therefore we're carrying an option of going essentially directly to Mars or Mars first, with the possibility that along the way there would be a test flight to the moon of the Martian system, or perhaps a visit to the NEOs of the Martian system. The Mars, this is the next chart, 22. This doesn't have a number, right? The architecture to launch a piloted mission to Mars is substantially more challenging. It involves as many as 6 Ares 5 flights to launch the 2 cargo flights, one of which brings a ascent vehicle from the Mars surface, and one of which brings a Mars surface hab. Then when that's all in place, as many as about 3 Ares 5 flights and 1 Ares 1 crew launch, bring the piloted vehicle, which goes to Mars, loiters in orbit while the crew goes down to the surface for over 500 days, and then returns. We've created a variant of this on the next chart, which is what a dress rehearsal for this would look like on the lunar surface, and convinced ourselves that if you were in fact to go directly to Mars or Mars first, that such a flight would be a reasonable idea, but it would be a test flight. It wouldn't have as objectives explicitly to put humans on the moon or to explore the moon. Its objectives would be to validate in a off-Earth environment the systems that would be used to go to Mars. And the timeline of this is significantly more extended because of the timing of answering both technical questions, such as what is the right aerodynamic shape to use in a Mars entry, descent, and landing system, or a Mars aerobraking system. You see that in there in the middle below the line around year 7 and 8. There would be more robotic landings, including likely a robotic sample return mission to assure to deal with issues of forward and reverse contamination from the Martian surface. And it would lead to first humans on Mars well into the second decade of such a program. The last of the destination options, chart 25, is the one we call flexible path. Here, essentially, the strategy is to extend human presence beyond LEO by visiting locations within the near-Earth space up to and including flybys and orbits of Mars, but not immediately go to the planetary surface. Now, it turns out that there are both programmatic and technical reasons to do this. The programmatic reason is that the steps necessary to get to the planetary surface, to build the modern-day LEM, to build the modern-day rover, to build the habitation and power systems, in fact, produce significant budgetary wedges in the program. So in essence, what this plan is one where we develop experience operating beyond LEO by visiting some interesting places and some near-Earth objects and doing flybys up to and including flybys of Mars, while we are at the same time developing the capability within reasonable expectation of budget to explore planetary surfaces, and then go back and go and explore the lunar surface. So the in-space part of it would look something like this, that there's first a lunar flyby-like mission. There would be then missions of up to the 20s of days to the near-Earth vicinity, the Lagrange points where the gravitational influence of Earth and Mars are balanced, which are potential sites for future exploration systems, such as fuel depots, and are potential sites for future servicing missions of scientific spacecraft that might be brought to those points for servicing. Then there would be to go to the Earth-Sun tipping points, the libration points, for example, the L2 point in the shadow of the Earth from the Sun, which is a likely location for many future astronomical observatories, or the L1 point between the Earth and the Sun, which would be the first time that humans would travel not only outside of the magnetosphere of the Earth, but outside of the bow shockwave of the Earth in the solar wind, and therefore better characterize and understand the physiological effects on humans of a true deep space environment that would be necessary for transit to Mars. By that time, you would build the capability to do a Mars flyby and potentially an inner solar system orbital flight like a rendezvous with Mars, Phobos, and Mars's moons, Phobos and Deimos.
Ed, just a clarification, don't we subsequently call this deep space?
We do.
Okay.
We have unfortunately used both deep space and flexible path to characterize the name of this. Good point. Chart 27. This is the equivalent flow diagram of this mission option, that there'd be unpiloted lunar flights and piloted lunar flights, and then some flights of increasing days up to 90 days. 90 days is approximately 10 times longer than any humans have ever been outside of the low Earth orbit. So this is not an insignificant accomplishment. Then a flight of maybe 180 days to one or several near-Earth objects. These are the objects which are on crossing paths with Earth that have both scientific and planetary protection implications, that understanding their trajectories, their composition, would be important for several reasons. And then we've basically shown in this diagram a branch off onto human lunar return by about years 7 or 8 into the program. 7 or 8 from the beginning of the piloted test flights. So what I just took you through was, now on chart 28, what I just took you through was 5 key decisions. What we do with the shuttle, what we do with the station, what the U.S. heavy launch capability should be, what the U.S. strategy for getting to low Earth orbit with crew should be, and where we should go beyond low Earth orbit. And for each of those 5 decisions, I described several choices that a policymaker would have, some of them as few as 2 choices and some of them as many as 4. What we did, both leading up to the last public meeting and subsequently, was we tried to create what we call integrated options. These are ways to string together these choices of each of the individual choices, the decisions about each of the individual choices, in such a way that it produces a package that makes good sense. And then to examine these integrated packages, these integrated options, both from the technical perspective, which I will not say any more about, and from a cost and schedule perspective, as Dr. Ride will speak about next. So I'll just take you very quickly through the integrated options, and this is the handoff to the budget and schedule discussion. The first one is, and the highlighting in color on this chart is intended to just sort of flag up what it is that changes, the principal change from one row to the next. So the first row is the program of record as I described it, not constrained to the fiscal year 10 budget, shuttle retiring in 11, station retiring in 15, launching with the Ares 1 and Ares 5, crew on Ares 1 and Orion, going to the moon in a sortie and outpost. We then constrained that in an attempt to get a program that would fit within the president's budget to be constrained to the FY10 budget. That's the second integrated option. The third integrated option is one which otherwise leaves the program of record largely unchanged and only extends the space station date to 2020. We examined that with Ares as the launch, Ares 1 as the launch mechanism to low Earth orbit, and with the commercial launch to low Earth orbit. And then we had one other variant which goes to the moon, but is extends the shuttle life and bases government launch services on the shuttle-derived vehicle. So these are, you can see, different combinations of ways in which you would eventually get to something like a lunar outpost, but by considering different combinations of shuttle extension, station extension, and some modest changes in the launch vehicle. The second set are the ones that basically go into the flexible path or deep space option, so that the common thing here on the right-hand side is the destinations and the strategy for exploration, going to lunar orbit, the Lagrange points, the NEOs, a Mars flyby, and then to the moon. So the first one is what we call dashed out of LEO. It's constrained to the budget. The shuttle retires in 11, the station in 15. We go directly to the Ares light, bypassing the Ares 1, and use commercial crew capability or the commercial delivery of crew to LEO. The one we call deep space option is not constrained, extends the ISS, and uses the Ares 5 light. The one that we call deep space EELV relies on building a commercial hydrocarbon 75-ish ton to LEO class vehicle. And the last one does much the same thing, except swapping out the shuttle-derived vehicle. So as you can see here, these are principally changing in and out. The heavy launch vehicle is the thing that's principally changing here. And the last three are arguably the ones that are either slightly or completely focused on Mars. That is to say that there's lunar sorties and extended stays, which are intended to be in a more Mars-like exploration preparation strategy. And here again, the principal change is the swap out of the commercial hydrocarbon vehicle with the Ares 5 Lite. And the last one is the Mars First strategy of not going to the moon, but planning on focusing and building systems to go exclusively to Mars, but reserving the possibility that we do a test flight on the moon. So that summarizes the technical considerations that have been underway and the refinements that have been made. And now I'll hand it off. Or Norm, do you want to have a discussion, or?
I think what we will do is ask you questions we have, and with regard to the possibility of adding options or deleting options, which is something I hope we can consider seriously here, we'll do that after we've heard the cost part, probably. But before you leave, I've got some questions. Does anybody else have questions they want to raise? Okay, fine. I saw you first, Jeff, and then Chris.
Okay. This is as much comment as question. I, in particular, because of the ties I have in the commercial world, have been getting an awful lot of questions from people going, why aren't we all excited about a lunar base because we want to do in-situ propellant production? A sentiment with which I'm in total agreement. And you have to really dive down into the details of what was envisioned for the lunar base scenario to realize that while we might want a lunar base to do in-situ propellant production, it wasn't this lunar base. This lunar base was proceeding in a very rapid fashion and very reminiscent of ISS to get the capability up there. Maybe we'll do some science with it, but we'll fundamentally think about what we're going to do with it and why it's there later. And that's the reason why it's in fact my advocacy of wanting to do industrial development on the moon that has pushed me very strongly in the direction of the lunar global scenario, because that way we do exploration and we build up a transportation infrastructure that we can do lots of things with while we find out what's up there and figure out what the things are that we want to do.
Good comment. Chris?
Ed, I just wanted to note that some of your flexible path slides show, as was the case the last time we saw these in, I think, Cocoa Beach, show Venus as a possible destination along the flexible path. And I wanted to note that from my point of view, I think that Venus makes very little sense as a destination for human missions and would be a terrible distraction from those destinations that do make sense, mainly Mars and and Moon. So I would recommend that Venus simply be dropped from all the deep space and flexible path scenarios.
Does anybody have a problem with that?
Yeah, I agree with that.
Yeah, I think it's probably a good idea, too.
Norma had a question.
Yeah, please, Wanda.
And in your Chinese menu of, a little shuttle, a little station, a little exploration, you didn't explicitly talk about technology except for the propellant options. I think that one of the things that, I'm concerned about is in order to do some of these hard things does require a investment in tech development and maturation and with an eye toward the actual application. So I guess my question to you for clarification is, what are your assumptions about the tech investment that's associated with each of these options?
Right. Thank you for flagging that up. At Cocoa Beach, I think it was, Jeff made a presentation as part of our working group on the high priority items, many of which are in fact enabling of some of these routes. The large high thrust blocked kerosene engine, the fuel transfer, some of the technology of planetary encounter. I'm trying to think what else were the main items on the list.
Advanced space propulsion of one kind or another.
Advanced in-space propulsion, restartable long cold soak, restartable engines, which are not of interest to really anybody but NASA. That is to say, they don't. It's not a pertinent problem on launch off of the Earth. and a similar list of things. That was in our Cocoa Beach presentation. And you're absolutely right. There has to be three things that are consistent here. One is the dedication of NASA and the highly trained and expert workforce of NASA to work on these problems. The second is their linkage to the future plans for exploration. And the third is their linkage to the budget. And we have recommended, as you'll see in Sally's presentation, which has been adopted in, I think, all but the program of record reference case, what we would consider a fairly robust technology investment program that would not only directly serve the needs of Constellation, but the longer-term needs of, not only the near-term needs of Constellation, but the longer-term needs of exploration, and also the needs of a burgeoning commercial space community. Needless to say, in addition, from a perspective that you would say, consistent with the Space Act of 1958, the development of technologies which are also of interest to the security interests of the nation.
Other questions?
I have one more question.
Sure, Bo.
No. You know, when I look at these options, Ed, we have these options or different selection of the launch system that will support these integrated options. And when I, for example, look at Ares 5 Light versus, for example, Shuttle Derived or the hydrocarbon rocket, what this doesn't really reflect is additional mission complexity that you have to face when you use more than one or more than two rockets. And you know, if you just observe what it takes to launch Shuttle or any of the other launch vehicles, you get affected by winds on the ground, winds aloft, lightning, a little failure, little glitches in the eco sensor, and God knows what else. So the more rocket you have to launch, is more difficult is to execute a mission. And I'd like to hear your opinion. What do you think? What is that element of increasing of mission complexity when it goes to smaller rockets? And would you agree with me that for a big trip, you need fewer big rockets? You know, when I saw your picture going to Mars, and I saw half a dozen of Ares 5, I think you
closer to a dozen of Ares 5, actually.
You probably couldn't put enough smaller rockets on this page, and not to mention how you would manage this scenario, you know, when you have to watch weather, watch all the other restrictions, watch hardware integrity to be able to execute these very many multiple missions. So could you address that mission complexity resulting from a large number of smaller launch vehicles?
I'll be happy to, and then I'll invite comment from anyone else on the panel. But you're right. If one moves to a smaller launch vehicle, one has to consistently make go down one or two routes. You either have to downsize the size of the in-space systems that you're going to use, or keep the same size in-space systems and developing a very capable in-space refueling, which introduces a certain type of in-space complexity. We do not think impossible, but not likely to be easy. Or you have to go down the route of having more launches from the Earth of call them slightly smaller heavy lift launch vehicles, which causes the complications of additional pad availability, range availability, weather issues, and so forth. And we actually had, in the course of the last couple of weeks, NASA do an analysis for us of basically launch availability when some number of critical payloads, some number of critical launches, and some number of less critical launches had to be flown within a certain window of time. And as exactly you expect, as anyone who's ever watched the shuttle try and fly, the more launches of vehicles that you need to get within a window, the more that impacts the total mission availability. Without going into the details of what the trades are, but one of the things that we did notice in this is that we will rediscover soon something that spacefarers knew in the 60s, is that if you're aboard in the ocean, there's an additional factor of sea state that comes into play as well, and it's been a long time since we've thought about sea state on that is to say how stormy it is in the ocean, right? It's been a long time since we've thought about that, but it won't be long before we start thinking about it again. And that too plays into the consideration of the human element of the launch, regardless of how the launch goes. So you're right. You either have to sort of downsize the things that you throw away from the Earth, or you have to invest in the refueling technology, or you get more launches, or some combination of those things.
Thank you.
Yes, I'd like to take your invitation to comment further. Ultimately, we want to be able to do bigger and better things in space. And I don't think anybody thinks that we're going to go to Mars someday with one really big rocket. So you ultimately, it's not a question of what you need to learn to do. It's ultimately a question of what order you need to learn to do it in. Either we learn how to put more things together, which lends itself to less large, I won't call them small, rockets. And that involves both an investment in technology, and that involves an investment in learning the things you need to learn to support a higher flight rate. And there's many of them. And again, as you said, and you look at the Mars infrastructure, it's not as though we're not going to launch 6 or 7 or 8 launches per mission on the current plans. The difference is cost is an independent variable. And it is not obvious that all of the ways of doing this also cost the same. It's also not obvious that we're ever going to go to Mars. Well, actually, it is obvious to me that we're not going to go to Mars with the current technology suite. So we don't know how many pieces of what size we're going to need to go to Mars. So I just don't think it's true to say that we know, as you stipulated, that you have to have a really big rocket to go places. I think that's one of the options. But it is not obvious that it's the best option, and it's certainly not true that it's the only option.
Sally?
Yeah, I wanted to just pick up on something that Ed mentioned. Ed brought up that we'll be landing in the water again with the present plan for Orion, and that opens up to me the whole issue of operations costs. We haven't really had a robust discussion about the size of Orion. It's the size of Orion with the 5-meter capsule that actually drives you to the need for a water landing. Were the capsule a smaller capsule, you'd at least have the opportunity of considering a land landing. I know both Leroy and I would prefer to land on land if we got to choose. But I think that maybe more to the point is that a water landing probably significantly increases the operations costs that you'll be facing with the vehicle for years and years and years and years into the future. And that's just one small example of our collective tendency to optimize programs for the DD&E cost, the DD&E phase, but neglect or push off till the future discussion of the operations costs and trying to optimize for the ops phase. That's gotten us into trouble before on the shuttle program, on the station program, where the ops costs just became what they became once we were able to launch the shuttle and once we were able to begin operating the station. And it would appear that we're in danger of heading down the same path with the current program or any program that we might elect to evolve into. And I think that I would argue that we should put a lot more thought, NASA going forward, put a lot more thought into the operational costs of whatever suite of vehicles and elements we go forward with, because it's those operations costs that once you're finished with the development, you're stuck with for 10 years, 20 years, 30 years, 40 years, and especially an exploration program, you're going to be facing those costs for a very long time in the future. So it really pays to consider them in the development phase of the program.
Well, thank you, Sally. Ed, I've got 3 items I'd like to raise, and then we'll, I think, move ahead into costing. The first is a net, and that is the program of record. We need to fix the chart to show it's 2010 on the shuttle here. The second is that the integrated options, the first 2 of them, really ultimately enable a trip to Mars, I think. And the document here makes it sound like they're sort of dead-ended after the flybys and so on. Mm-hmm. If I'm right, we ought to do something to make clear that there's another phase beyond this. It's just beyond our costing and lifetimes, I'm afraid. The third one is kind of a catch-22, where, as you were describing the first block of options, you had mentioned that if you had a shuttle-derived vehicle, it would make sense to keep the shuttle operating, which makes some sense to me. On the other hand, if you keep the shuttle operating, you won't have any money to build the shuttle-derived vehicle. And would you care to comment?
I think that's an excellent introduction to Dr. Ride.
Okay. You're on.
And I was just going to ask Sally, you know, that it doesn't make a difference to you that it's off San Diego?
Well, actually, as a matter of fact, it does make a difference to me that it's just off San Diego. So I'm hoping for precision in the landings. Norm, let me just, before I get up, briefly address that question, because we're about to get buried in numbers, and I think that's a good question to discuss. As you'll see in as part of this, or as I'm sure will come out in the discussion, the costs of NASA's existing infrastructure, facilities, workforce, capabilities are a real important consideration actually in all of these scenarios, because in some cases you're able to keep them, in some cases you keep them to a significant extent, but you have to reconstitute the workforce. When Shuttle retires, there will be a significant disruption to the workforce. Other of our options require less of the NASA infrastructure, and there's one in particular that actually envisions a completely different model that would bring with it significant disruptions to the NASA, the existing infrastructure. So we're going to see that play out. The combination of the shuttle and a shuttle-derived vehicle takes maximum advantage of the existing facilities, the existing infrastructure, the existing workforce, the existing elements. So in some sense, those costs are shared by the shuttle and the shuttle-derived vehicle. So there is some savings. That's not to say that it's necessarily the most cost-effective program, but there are savings that way. And in fact, there are actually some savings just going directly to a shuttle-derived vehicle, again, because it's got the most commonality with the existing infrastructure and facilities. Okay. But we're gonna see this play out in the costing. So
thank you.